Okay, so now let's start our introduction about continuous random variables. At the beginning, you may feel it's a little bit abstract, but we will try to help you get the most important ideas, and we will try to avoid those mathematical properties. Yeah. Anyway, yeah, let's do this. So some random variables are continuous, and as we mentioned 2 weeks ago, if a variable is continuous, that means the value should be measured instead of counted. Or more intuitively, the possible values together form an interval instead of a discrete set. So, some examples. If we are talking about a particular time point as the next lecture starts, okay? At that moment, if we count the number of students in our classroom, it's random and it is discrete. Okay? The number of students is discrete. But if we are talking about the temperature of our classroom at that particular moment, then the temperature should be continuous. Okay? Because we cannot count what's the temperature. We can only measure how high the temperature is. Okay, so this is a simple example about whether a value is measured or counted. For a continuous random variable, typically those possible values will form an interval or lie in an interval. As the example of temperature, suppose we let x be the temperature measured in Celsius. Let x be the temperature of our classroom at that moment. Then one interval that I believe can cover all the possible values of x can be 0 to 50. Okay, it's basically impossible for the temperature to be outside this interval. So in this case, we can say this particular interval contains all the possible values of our random variable x. Okay, and in particular, x may be any value within this interval. So of course, if you think about the practical situation, this interval may be too large. Okay, so probably that's basically because I am very conservative. Some other more reasonable ranges may be, let's say, 10 to 40. Okay, that's also very reasonable. Okay, but the point here is not the size of this range. The point is that all the possible values together form an interval. Okay, the temperature may be 20, maybe 20.8, maybe 20.825, something like that. Okay, as long as our temperature meter is precise, is accurate, we can say that possible temperature is not really discrete, it's continuous. Okay, so that's the idea. When we have that kind of measure about our temperature, of course we may be we may be interested about knowing the following quantities, like what's the probability for x to be 20. Okay, so typically 20 degree for myself is the most comfortable temperature, and if I can work or I can teach in the temperature like this, I would be very happy. Okay, so I probably want to know what's the probability for the temperature to be 20. Or if 20 is not happening, I'm quite okay if the temperature is within 18 to 22. In this case, I am still very happy and I would be energetic in the class. So I would like to know how likely the temperature would be within this comfortable range. If the temperature is really high, it's very bad. Or if the temperature is very small, it's very bad. So I probably want to measure these probabilities. Okay, and obviously these probabilities help me to make better decisions. For example, about what to wear, or about what to prepare in advance. So, that's just one example. Let me give you another example about continuous random variables. Suppose I ask you about how many courses do you take in this semester? Okay, how many courses? Immediately you think, how many courses? This can be counted, so this should be discrete. That's true. But let's see what I want to tell you. Suppose we label all the students as number 1, 2, 3 up to n. And suppose I say xi is the number of courses taken by student I. Then, as we mentioned, xi is discrete. But the mean of all these numbers is basically continuous. Okay? Some students may be taking no course, at least one, maybe one course. Some students may be taking 3, some students may be taking 4. Anyway, their average or their mean number basically can be treated as continuous, right? Even though we really know there is a finite number of possible values, but because there are so many values within a small range, we can say it's a continuous, or we basically say it's a continuous random variable. Okay, so as long as you have a large denominator, then your mean, sorry, I made a mistake again. This should be sum of divided by small n. As long as you have a large denominator, then your average or your mean number of anything basically would become continuous. Okay? So that tells us why continuous random variables are important in statistics. Because in statistics, mean or average or expected value is just the most important measure in statistics, as it must be basically continuous. We need to get enough knowledge about continuous random variables. Otherwise, there is no way for us to study the property of mean values, the properties of anything else. Okay? So I hope that's motivating enough for you to keep going on studying continuous random variables. Okay, so we need to know something about continuous random variables, but it's just so abstract. So let me start with a discrete random variable, and then I will show you the connection. Again, let's try to roll a dice. Okay, I will roll a dice. Suppose I roll a fair normal dice, then possible values are 1 to 6, and for each of them I know the probability is 1 over 6. Okay, so that's the 6 dots on the graph. For each of them I have a probability that is roughly 0.17. Okay, so that's nothing special. Suppose my dice is special and it has 12 instead of 6 faces. Then, if it's still fair, then I know the following. First, the sample space or the collection of all possible values now is enlarged. It contains those fractional values 1/2, 3 over 2, 5 over 2, and so on up to 11 over 2. Now I have 12 possible values, and obviously, for each possible value, the probability now is just 1/2 of 1 over 6. Now it's 1 over 12. Okay? So those are the red dots here. You can see that we have 6 more possible values, but the probability for each value to occur becomes just 1/2. I mean 1/2 of the previous probability. If we do this kind of splitting even further, suppose I roll a dice that has 24 faces, then I would have 24 possible values, and for each value the probability to occur, for that value to occur, is just 1 over 24th. Okay, the blue dots here. So obviously I can do that even further to get a dice with 40 faces, 100 faces, or 1000 faces, and so on and so on. I can keep increasing the possible number of possible values, and then for each value the probability will be smaller. So if I really have a very large number of possible values, then for each possible value, that probability should become very close to zero, right? If I have 100 values, then the probability is 1 over 100. If I have 1 million numbers, then the probability is 1 over 1 million to get each value. So, if I am really talking about a continuous random variable, continuous random variable whose value is within 0 and 6. Okay, if I am really talking about this, then I know all those values within 0 and 6 may occur, but the probability for us to see exactly a certain number should be 0. Okay? So in general, for any continuous random variable x, no matter what's the value you assign to it, the probability for seeing x to be exactly that value can only be 0. Okay? Basically, it's just because the total probability can just be 1. But if you have infinitely many possible values, then each value can only have a 0 probability. So that's one thing. Probably you feel this is somewhat weird, right? Because all the values may occur, but the probability for each value to occur is 0. So that sounds contradicting. But later I'm going to use the next video to tell you what's really happening with that statement or with this kind of continuous random variables. Thank you.